Hi everyone, my name is Alicia Ukani, and I'm a PhD candidate at UC San Diego. Today I'll be presenting our work, Local Frames, Exploiting Inherited Origins to Bypass Content Blockers. This work was done in collaboration with Hamid Haddadi and Peter Snyder at Brave, as well as my advisor Alex Noren. In this talk, I'm going to show you how most websites can easily bypass popular content blockers, and that over half of popular websites currently have the capability to do so. I'm going to start with some background about local frames, origins, and content blockers, before diving into the 4 core capabilities of popular content blockers. Then I'll discuss how we can actually evade these capabilities through local frames, and then discuss our measurement study of local frame prevalence before concluding. So let's start with local frames. A local frame is simply an iframe with a non-standard source like about blank. Now normally iframes are used to pull in third-party content, but here you can just think of it as a wrapper, where you can dynamically add your content and then have a very useful isolation mechanism. Local frames, like all iframes, get an empty HTML document, no CSS rules, a clean JavaScript environment, and so this is great for isolating certain code in your first-party website from the rest of your content. Now let's get into origins. An origin is defined as a protocol, hostname, and port. So for example, the origin of https foo.com/bar would be https foo.com with an implied port of 443. Now, origins are often discussed in the context of the same origin policy, which protects users from potentially malicious embedded content by saying only content with the same origin can access each other. But we're going to consider it in a slightly different context, which is content blocking. Often content blockers are deciding whether to allow or block a certain network request by determining whether it's made in a first-party or third-party context. Now, in order to determine that, you need to understand the origin of the request source and destination. Now, normally, the origin can be derived from the frame's URL. So in the example I showed you with https foo.com/bar, we could just use that URL to derive that origin. But it's a bit more complicated for local frames, because local frames actually inherit the origin from their parent frame. So let's go through an example. Let's say we're browsing on foo.com, and we have an iframe pulling in content from a third-party bar.com. If we write some JavaScript code and execute window.location.hostname and window.origin, they both return the same value, which is bar.com. So it might be really easy to think that these two properties are equivalent. But if we consider a local frame and we execute window.location.hostname, we actually get an empty string, because what's the hostname of about blank? However, if we were to execute window.origin, we would then inherit the origin from the parent frame, which is foo.com, and get that value. So this just shows how easy it is to handle local frames incorrectly. If you're not thinking about them, you would think these two properties are the same. And we find that many content blockers make this exact same mistake, and so they can be bypassed in local frames, but we'll talk about that later. Now let's actually talk about content blockers. Content blockers are tools that can hide ads as well as any unwanted content. They can block tracking scripts, reduce mobile data usage, and they're extremely popular. I've listed a few of the top content blockers here. So we've analyzed the capabilities of content blockers and grouped them into 4 different categories, which I'll now dive into in more detail. To illustrate these capabilities, I'm going to walk you through an example website. We can see that it has an ad on the left-hand side, and then as also a tracking script. The script first needs to be requested from another website, track.com, which will then return the script, and once it loads and executes, it'll perform canvas fingerprinting. Here, canvas fingerprinting is an example of a just privacy invasive behavior, and it works by accessing the JavaScript Canvas API to render an image that is often hidden from the user. And on different people's computers, this is going to generate a slightly different image, and so it can be used to generate a unique identifier. So let's start with the first capability of content blockers, which is request blocking. If a content blocker is installed and wants to protect this user's privacy, they can simply prevent the website from requesting this script, so it never gets returned and never executes on the page. So this is very effective, but also a little heavy-handed. Let's say that script also included some important variables that the page actually needed to access. Now, if we never let the script execute, then we're not going to ever define those variables, and the page may even break. So this is the motivation for the second capability, which is called resource replacement. Instead of outright blocking that script, we could redirect it into a benign version. So for example, we could change this network response to have it return an empty JavaScript file instead of this tracking script. We could also redirect the script into another version that defines those important variables that the page needs to access, but not actually perform that canvas fingerprinting. The next capability is called scriptlet injection. Scriptlets are pieces of custom JavaScript code that these content blockers inject into the page. So scriptlets can do a variety of things. They can remove cookies, they can disable access to certain JavaScript APIs. And so in this case, we could prevent access to the Canvas API and therefore prevent Canvas fingerprinting from taking place. Finally, the last capability is cosmetic filtering. This capability uses HTML and CSS selectors to find something on the page and simply hide it from the user's view. So for example, we can make this ad disappear. So now let's talk about how these capabilities can actually be evaded through local frames. So in our work, we designed a bunch of test web pages that specifically isolated these capabilities and tested whether they behaved correctly inside of local frames. So for request blocking, we made a test page with different local frames, and in the local frames, we tried to request a certain resource. Then we systematically downloaded different content blocking tools, added filterless rules to try and block that resource from being requested, and checked if those requests were actually blocked. For resource replacement, we chose a representative example of AJAX asynchronous requests to be redirected. So again, we created a bunch of AJAX requests inside local frames. We set filterless rules in different content blocking tools to try and redirect the response of that request, and checked whether that redirection was actually successful inside of local frames. Similarly, for scriptlets, we chose a representative example of setting a property of the window object, and we checked if that window object was successfully set inside of local frames. Finally, for cosmetic filters, we checked that if we try to hide an element in a local frame, is it actually correctly hidden? So through this analysis, we found 19 different vulnerabilities across 6 different content blocking tools. We found that all of the tools that offer cosmetic filtering as a capability had a vulnerable offering. We also found that all of Brave's iOS protections could be bypassed through local frames, and later we'll talk about why Brave iOS was vulnerable to request blocking evasion. Now, we disclosed all of our findings to the affected parties. So our work led to patches in Brave, Apple, AdGuard, DuckDuckGo, and uBlock Origin Lite, where we collaboratively worked on that. And so ultimately, 15 of the 19 different vulnerabilities that we found have been patched. So now I'm going to go into a few case studies of some of these patched vulnerabilities. Let's start with AdGuard. AdGuard was really interesting because they computed the origin of a third-party local frame to be the first-party website. Now this has 2 main consequences. The first one is evasion. So all of the rules that were meant for the third-party website were not being applied to that third-party local frame. So this means that any tracking resources that were requested in the frame would not be blocked. The second consequence is potential breakage. So all of the rules that were meant for the first-party website were now also being applied to this third-party frame. And so it's likely that the developers did not test those rules on this third-party website, and this could cause some breakage. In addition, AdGuard had this miscomputation for scriptlets and cosmetic filtering. And scriptlets are really powerful, and they can disable standard web development tools like event listeners. And so the possibility for breakage is magnified. The next case study is the Safari Content Blocker API. This API was introduced by Apple. Apple was concerned about apps being able to view network traffic, but they still wanted to allow content blocking apps, such as on iOS and Safari extensions. And so Apple created this API that would let these extensions define their own filterless rules, but then Apple would actually enforce them. We found that this API was vulnerable to evasion for cosmetic filtering. And so this means that all of the apps that were relying on this API were also vulnerable. And so this could have significant downstream effects. Our next case study is Brave. Now, Brave is a privacy-forward browser that tries to comprehensively protect users from tracking. But the more code you write, the more code complexity you have, and therefore the more opportunities for evasion you can also have. So as an example, Brave iOS was using that Safari content blocking API to protect users from standard network requests to trackers. But that API did not cover asynchronous network requests. And so Brave introduced an additional code path to protect users from asynchronous network requests to trackers. But in that code path, they had a bug where they weren't properly computing the origin of these requests, and so they were able to be evaded through local frames. Our last case study is DuckDuckGo. Now, DuckDuckGo actually couldn't be evaded. They correctly blocked network requests to trackers that were made not only inside local frames, but also local frames nested inside each other, so that's great. But they still had a bug. DuckDuckGo has a feature where they report to the user the number of tracking requests they blocked. So even though they would block these requests to trackers inside a nested local frame, they wouldn't actually report that back to the user. And so the user may not know about the privacy-harming behaviors of the websites they visit. So this just goes to show that even if a capability can't be evaded, there are still so many subtle ways to incorrectly handle these types of frames. So I'll again note that all 4 of these case studies have been patched due to our work. Let's get into the last section, which is our measurement study of local frame prevalence. We conducted a large-scale measurement study crawling almost 22,000 websites from the Trenco list of the top 1 million most popular websites. We measure not only how many local frames there are, but also the behaviors happening inside them, such as the network requests they make, the JavaScript API calls, including fingerprinting-related ones, and the HTML elements created inside them. We found that local frames are extremely widespread. We found them on over half of the websites we crawled. And also that 62% of websites with local frames were making requests to tracking resources inside of those local frames. And this represents 14% of all websites we crawled. In addition, over a third of websites with local frames were making calls to fingerprinting-related APIs inside them. And lastly, we looked at which third-party entities were creating third-party local frames, and we found that they were primarily analytics and advertising companies. So to conclude, we found that local frames are extremely widespread and could evade content blockers. But our work has led to patches in Safari, Brave, AdGuard, uBlock Origin Lite, and DuckDuckGo. Now, what I hope you take away from this talk isn't that we found some cool new evasion technique, but really that the web is complex, and developers need help in navigating this complexity. I think it's very understandable to make these subtle mistakes, but the more support and resources we can provide to these developers, the easier it will be for them to handle these sort of complex cases. So thank you so much for listening. You can find links to our paper as well as all of our code and data, and feel free to contact me if you have any questions. Thank you.